last Wednesday about a law called Coulomb's law that provides for us a relationship between electric force of attraction and repulsion and charges. How much force of attraction and repulsion we have between those charges a certain distance apart from one another. We learned about an experiment called the torsion balance experiment that was used to derive that equation. What does the word torsion mean? Sorry? Twist, yeah, twisting, torsional properties, or the twisting properties of something. We have a string that's attached to the top of a box or a ceiling here, and on the end of the string we have a rod, and on either end of the rod we have this object, this ball or whatever. One of them, let's say, is charged. We'll call it Q1. We bring another charge nearby it, we'll call it Q2. We get the blue one and we get the green one, charge 1 and charge 2. When we bring Q2 nearby Q1, what happens? One of two things will happen here. What are the two possibilities? Yeah, it's going to attract or repel. So number 1 is either going to be pulled towards number 2 or it's going to be pushed away from number 2. It doesn't really matter what happens because in either case, that string is going to twist. We're going to examine the torsional properties, of the twisting properties of that string to determine the force. You know that intuitively, the more you twist that string, the more force is required. That can be a measure of the force. Just like a spring scale, how much a spring stretches can be a measure of the force applied on something vertically. The amount of force that's applied on the string can be measured by looking at how much the string twists. If it twists 2 degrees, it was this much force. If it twists 8 degrees, it was that much force. We can measure the force by measuring how much the string twists. So we'll say that indirectly, Coulomb was able to measure the force of attraction and repulsion simply by looking at how much the string twisted. He's also able to measure R. This is the easy one, right? The distance that separates those two charges. Use a ruler or something like that, right? Or something that measures distance. And he's also able to kind of indirectly measure Q1 and Q2, the two charges involved here. He wasn't able to measure the charge in coulombs because, well, the unit for Coulomb didn't exist before Coulomb, right? Like, he only got a unit named after him because of all the work he did with electrostatics. It wasn't named after him before he did anything. There was no unit for charge here right now. So what he does is says, look, I got a charge, let's call it 1. I got a charge of 1. 1 what? Let's call it random units. Okay, I'm making that term up, not him, but 1 random unit of charge, whatever that charge is. Now, if I touch 1 random unit against a neutral object, what are they going to balance it to be? 0.5 random units. So this guy that was 1 random unit becomes 0.5 random units. And then I touch it against a neutral thing again, it becomes what? Yeah, 0.25 and 0.25. And so on, right? So you can see here, without knowing how many coulombs the charge is, we can still measure the charge in random units, which is good enough for us if we're just trying to find a relationship between variables. Does that make sense? So now we got the force measured by the amount of twisting in the string. That's going to appear as a test question later on down the road, by the way. Okay, what does the twisting in the string represent? The amount of force of attraction and repulsion. We can measure the distance, we can measure the charge 1, and we can measure charge 2. We performed 3 experiments. In the first experiment, these are the results we get, F versus Q1. What would be the manipulated variable in this experiment if we're plotting F versus Q1? Yeah, Q1. What's the responding variable? What is it? Somebody said it? F, yeah. We always know what manipulated is and what responding is by the graph, right? Manipulated is always on the x-axis, responding is on the y-axis. This gives us a straight line, which tells us the relationship, or better told Coulomb, the relationship is this. F is related to Q1. You guys seen this symbol before, this little alpha symbol for proportional? Have you seen that? Some have, some haven't. Okay, it's always mixed. Who's seen it and who hasn't. It's not a big deal. All it means is that if F is proportional to Q, then when something happens to Q, the same thing happens to F. If Q doubles, F doubles. If Q quadruples, then F quadruples. Does that make sense? They're linearly related to each other. Okay, the next experiment was F and Q2. Q2 would be the, oh, sorry, I forgot to ask you this. What are my control variables in the first experiment? Manipulate Q1, F responds to that. What are my control variables here? The important ones, that is, not all those other silly little ones that nobody really cares about. The important ones now? Good. Q2 and R. We got to keep all Q2 and R the same, otherwise, who knows what caused the results that we see, right? Q2 is manipulated now, F is responding. What are the control variables? What has to stay the same? Q1 and R, right. The relationship there we're going to say is, well, it's a linear relationship as well. F is related to Q2. And finally, this is the one that you're going to plot. This is the one that you'll plot in the activity that you're going to do tomorrow. F versus R. Okay, R being our manipulated variable, Q1 and Q2 being our responding variable. The graph's going to look like this. Now, if you were to interpret that just by looking at the graph, you might interpret it as this relationship. F is related to 1 over R. And although that's not technically correct for this graph, it's pretty difficult just looking at it with the naked eye to distinguish between the graphs that would be produced by 1 over R and 1 over R squared. So it would be either 1 over R, or as it turns out to be in this case, that shape would be 1 over R squared. Now, Coulomb recognized all these relationships, decided, I'm going to put them all together. It says F is related to Q1, and it's related to Q2, and it's related to 1 over R squared. Well, if it's related to all of those, then it must be equal to a constant, a number, times all of those. Right? We would say in a graph that looked like this, y versus x, we would say y is proportional to x, or y is equal to a number, a constant, times x, m being the slope, right, that constant. Okay, here we're saying f is related to Q1, Q2 over R squared. Well, it's equal to a number times Q1, Q2 over R squared. That number, by the way, is called Coulomb's constant, and its value is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. That looks a lot like that equation we learned last year called Newton's law of universal gravitation that says F is equal to the gravitational force is equal to big G M1 M2 over R squared. Does that ring a bell? G, 6.67 times 10 to the minus 11 Newton meter squared per Coulomb squared. Both of these we would call what? What type of relationships do both of these have? Yep. Yeah, inverse square, because the force is inversely related to the square of the distance. So as R gets bigger, F gets smaller, exponentially, right? If you double R, F goes down by a factor of 4. If you quadruple R, F goes down by a factor of 16. As they get closer and closer together, F gets exponentially larger and larger and larger. So they have that in common. They're both inverse square relationships. The equations look almost exactly alike. One of the differences, clearly, one uses mass and one uses charges, right? Another difference? Well, the electric force can be attractive or repulsive. Gravity, as far as we know, in this world, has always got to be attractive. So one of them involves attraction or repulsion. One of them involves just attraction. Which one's going to be bigger? Certainly in the context of the atom, when we're looking at, you know, an electron and a proton orbiting around, electron orbiting around the nucleus, whatever. Which one's going to be bigger? Yes. Yes. The electrical force is in the context of the atom is always going to be bigger, and a lot of times in larger contexts bigger as well. Okay? So certainly some similarities, some differences as well. Let's have a look at worksheet number 6 now. 3 questions on that sheet. Number 4, 5, and 7. Number 4 says, 2 identical charges are separated by a distance of 1 meter. A repulsive force acts between the charges. What's the magnitude of each of the charges? How can we find 2 unknowns with one equation? Well, let me answer that question, actually. You can't. The simple answer to that question is you can't. So what are we going to do about it?
We're going to take them as one.
Yes, they're identical. So we don't really have two unknowns. It's two charges, but they're both the same. So instead of calling them Q1 and Q2, let's call them Q. Let's call them both Q. My equation, therefore, becomes K times Q over R squared. Does that make sense? Or you could call them Q1 if you wanted, and just make them both Q1. Doesn't matter, as long as you call them the same thing. What's Q times Q? Yes, it's Q squared. A lot of people will say it's 2Q. Q plus Q is 2Q. Q times Q is Q squared. So this is my equation now. F is equal to K times Q squared over R squared. Now it's starting to make a little bit of sense. Solving for Q here, the R squared goes up by multiplying. F times R squared, K times Q squared. Divide by K. And then what are we going to do? Square root it, right? So Q becomes the square root of F times R squared over K. Does that make sense now? Do we need to, I can sub the numbers in there if we want, if you guys need me to, but if you guys are comfortable with where we're at here, then I'll just skip that. Good. Okay, the answer, by the way, worked out to be, what was it? 2.00 times 10 negative 5. Yep, good. Okay, number 5 gets a little bit trickier here. Electron and proton this far apart. What's the force? Oh, that's not so bad. What's the force between them? Well, we need to know the charges, but other than that, it's not bad. What's the acceleration? That's new. What's the initial acceleration at that? Okay, let's get the force first. We're going to say 8.99 times 10 to the 9, as always, times Q1, 1.6 times 10 to the minus 19, times Q2. They're both that, aren't they? Isn't the electron negative, though? You guys remember what I said on that podcast last Wednesday? If there's a negative, what should you do with it? Don't plug it in. Don't plug in the sign of a charge into the equation. If something's negative, leave it out. Let's worry about the sign let's worry about the direction of the force later on. Okay? Just sub it in as positive. You'll see why a little bit later today, why it's, in my opinion at least, so important to leave that sign of the charge out. R is, man, that's such a small number. Would we expect to get a big number or a small number here for the force? Those are small charges, but, man, is that ever a small distance? I would expect a big number for force here when you're that close together. What has a bigger factor? Like, we got small charges, and that's going to decrease the force, right? But we have a small distance, a really small distance. What's more important, the charge or the distance? Distance. How come? Because it's squared. So my gut is that we get a big number here, a big acceleration. In fact, we do. We get 8.22 times 10 to the 28 newtons. Okay, that's a really big force. Now, how do we find the acceleration? Well, who's a Star Wars fan here? Nobody? It's a class of physics 30 students and nobody's a Star Wars fan? Few people, okay. Just a little slow on it, that's all. The first Star Wars, it's called A New Hope, which wasn't called A New Hope at the time because it was just Star Wars at the time. Luke had the Force, right? The Force was with Luke. But what did he have to do? He had to learn to use the Force, right? Had a little help by Yoda. Yoda helped him out. Went into what was that place called where he crashed his X-Wing and what was that called? Was it? I still can't say it. Yoda showed him how to use the Force. Okay? When you want to find the acceleration of physics 30, you need the Force to be with you. Get the Force. Then you need to do a little Jedi training here, okay? Learn what to do with the Force, okay? Luke would have said, hey, I know the Force is 8.22 times 10 to the 28. Yoda would have said, Luke, Newton's second law you must do with the force. A is equal to F over m. 8.22 times 10 to the 28 newtons divided by the mass of the electron. And we get a value of 9.03 times 10 to the 58. Listen, if you're in physics 20, there were so many different equations you could use to find the acceleration. There is in physics 32, but 99% of the time, if you want the acceleration in physics 30, you're going to get the force. The force needs to be with you. And once the force is with you, you just got to do whatever with it. Okay, Yoda says divided by mass. And that'll give you the acceleration 99% of the time. If it doesn't work, all right, try one of those acceleration equations. But it's, for all practical purposes, going to work for you every time in physics 30. Okay, get the force divided by the mass. Now, what would I have done if I had been looking for the acceleration of the proton? Would it have been the same? How come? Emily, how come? Different mass. Good. Would the force have been the same? Yes. Object A applies a force on B. Object B applies an equal and opposite force on A. But that doesn't mean the acceleration will be the same. You take the same force divided by the mass of the proton. Good? Okay, let's take a look now at number 7, our last one here. Oh, let's erase that. Charge of 2 coulombs is touched with a second one of 6. Let's say then separated, then touched with a neutral object. Got that? So 1 touches 2, then they're split apart, and then 1 touches 3. Now what's the force between 1 and 2 after all that? The people that will do well in physics 30 are the people that will look at a question like this and not just look for an equation to solve it. Not one equation. Like they stop, and before they look for something to solve it, they think about what's going on. What's going on here? We've got charges touching each other, and then we want to find a force. So let's do the charges touching each other, and then let's find the force. Yeah. Yeah, that's a good question, actually. Yeah, similar size, similar shape. So that means they're going to balance out, right? So let's create our little table. Remember we did, like, I don't know, the second day of this unit, I think. Here's the 3 charges. Here's the total. We start off as 2, 6, and 0, adding up to give me 8. Now it says what? The first one, 1 touches 2. If 2 and 6 touch each other, what are they going to balance out to be? 4 and 4. 2 plus 6 is 8, divided by 2 is 4. So add them up, divide by 2. What do we end up with? 4 plus 4 plus 0 is 8. Looks like I've done that right. Then it says, what? The first one touches the third one? 4 and 0 touch each other? Dylan, what do they become if 4 and 0 touch each other? Yeah, 4 plus 0 is 4, divided by 2 is 2. And then we got 4 in the middle. Add these up. 2 plus 4 plus 2 is 8. Okay, it looks like I've done it right. The odds of me having made a mistake here are really small, given that I got the same total charge all throughout it. Yep.
Will you ever have to add up more than 2 and then divide by 3?
I doubt you'll have to do that, but it's conceivable. If you had 14 of them touching at the same time, then you would add them up and divide by 14. Yeah. Sometimes we get more than 2 or 3 or 4 objects even, but I don't recall a question in physics 30 where there's been more than 2 touching at the same time.
I just don't get how in this one you can tell like the first one touches the neutral one. Like I thought they were just still together, the first and the second.
Yeah, that's why I said then they're separated here, because in the original question I agree that wasn't worded well at all. Okay, it says this one is touched to a second one, then with a neutral object. With the way that that's written, it actually should be add them up, divide by 3. It's not what it was meant to be, but that's what it was written to be. Okay, you're right about that. Does that make sense? If that wording is there, then separated, does that make more sense? Okay. I mean, you can be confident on a quiz or a test or an exam that it'll be clear, right? I haven't made up that question. And so sometimes when you proofread your own stuff, you read what you want to read, right? But when it's a home exam question, that won't be there. Okay, now we want to find the force here between the first one and the second one. So let's say K, Q1, Q2 over R squared. 8.99 times 10 to the 9 times 2 times 4 over 5 times 10 to the negative 2. Let's square that. Let's do that on the calculator here. 8.99 times 10 to the 9 times 2 times 4 divided by 5 times 10 to the negative 2. I should have bracketed that, but if you actually do it properly with the EE button, you don't actually have to. 2.888 times 10 to the 13. Now, is that going to be an attractive force or a repulsive force? Emmerich, do you know if it's attractive or repulsive? How do you know? Yeah, both like charges, +2, +4. Doesn't say what's the magnitude. It says what's the force, right? So we should indicate a direction somehow. That it's a repulsive force. How about this one? Find the net force on B due to A and C. Well, let's name these. A, C, and let's name the middle one B here. The net force on B due to spheres A and C. Listen, if I only had two charges, I'd say F is equal to KQ1, Q2 over R squared, right? Or KQA, QB over R squared, right? Can I just change this? Can I change my equation up a little bit? Just the tiniest little bit. Can I do that? Never. Never. If Q1 and Q2 give me newtons, then Q1 and Q2 and Q3 cannot give me newtons. If you add another Coulomb into the mix, you can't get the same final units out of it. You can't just arbitrarily change an equation because it seems logical. Never. So what are we going to do? Yep. Yeah. Even before that, though, actually, there's something else I want to do before I calculate those forces. You're right, but it's something I want to do before that. Yes, change the units. Okay, should probably circle those, actually. Good point. Change those to coulombs. If this was a physics 20 problem, we had a force of A on B and a force of C on B, what would you do before you started finding the values of the forces? Draw a Freebody diagram, right? Let's draw a Freebody diagram for object B. Let's pretend C is not even there, okay? Let's pretend C is not there. A and B, that's it. Did they attract or repel? Pardon? They repel. How do you know? Because they're like charges. Good. If they repel each other, then B must be pushed away from A. I'm going to call this the force of A on B. My fab force. Force of A on B. Now, B also pushes A away as well, right? But I'm going to erase that because how come? I don't care. I don't care. I don't care what happens to A in this question. I'm looking for what happens to B in this question. So although there is another force there, on A, I'm drawing a Freebody diagram for B. Okay, let's now pretend that A is not there. C and B, do they attract each other or repel each other? Jason? Yeah, they're going to attract each other because they're opposite charges. Emma, is that if they attract each other, which way does B go as a result of that? Towards C or away from C? Yeah. It's pulled towards C. Now, C would be pulled towards B as well, right? But, David, we don't care. I'm going to call this FCB, or my force. Okay? My fab force and my, however you say that without a vowel. Doesn't matter what you call them, right? Call it F1 and F2. Call it FA and FC, whatever. I like to call it FAB and FCB because it tells us what's acting on what, right? A is acting on B, C is acting on B. Now, Bernardo, now what? Now we calculate those forces. And this part is easy, right? KQA QB over R squared. Two times 10 to the negative 6 times 3 times 10 to the negative 6 over 2 squared. It gives us a value of, I think, 0.013485. And then CB, KQC QB over R squared. Oh, wait a second. That 1 times 10 to the negative 6, that should be negative? No, drop the negative, right? Get a distance here is 1.5. Okay, before I ask you what to do with these now, look what would have happened if I had have put a negative in for the 1 microcoulomb. I would have gotten a negative force, right? What do you think the temptation would be to do? I would have gotten positive 0.013 and negative 0.011. What would the temptation be to do? Subtract them, right? Or add the negative of it, right? But that's not what I do. I got to add them as positives because they're both to the right. David's Freebody Diagram showed me that, right? That they're both to the right. This is why I don't want you to put a negative into an equation for charge, because it's just going to get messed up with sign conventions. For us, we get a negative force, it means left, not attractive. Attractive could mean left or right. We don't want it to mean left or right. We want negative to be left for a force. So I'm going to say the net force acting on B is going to be 0.013485 plus 0.01198. And I'm not going to get that mixed up. I'm going to make it positive for sure because I'm looking back to this to determine the direction, not the sign that I get when I sub in charges. This works out to, by the way, to be 2.55 times 10 to the negative 2 newtons. Let's set up now question 1A on worksheet number 7. We're going to solve this, but we'll just set it up here. So there's 3 charges in a straight row. First is 5, second is 5, third is negative 2.5. 1, 2, and 3. I'm just going to label them as positive, positive, and negative because I'm not going to solve this for you right now. I just want to set it up. Positive, positive, and negative. That's the important thing right now. Distances. This is going to be 0.025 meters. Make sure it's in meters, not in centimeters. This one's going to be 0.25. No, it isn't. What is it? 0.200. Right? Good? Okay, now when I said, make sure you draw a diagram, this is where some people stopped and said, there's my diagram. Well, what I should have said, I should have been more clear and should have said, draw your free body diagram. Is this a free body diagram? No. Free body diagrams show what? Forces. Does this show forces? Not at all. Not in the slightest. So let's pretend we're trying to find the net force on number 1 here. Let's pretend that number 3 is not there. Just 1 and 2 are there. 1 and 2, both positive. Attract or repel? Do they attract or repel? They repel because they're like charges, right? If they repel each other, then 2 is pushed to the right, 1 is pushed to the left. I'll call that F21, the force of 2 on 1 to the left. Now, what about this force on number 2 that I drew there? Right here? That I'm going to erase. How come I erase that? Well, I'm not trying to find the force on number 2. Not yet. Not in question A, right? That's later on. Okay, now pretend 2 is not there. What about 3 and 1? Do they attract or repel? Do they attract or repel each other? They attract each other because they're opposite charges, sorry. Right? So 1 is pulled towards number 3. We'll call that F31. It's attracted towards number 3. Now, 3 is pulled towards number 1, right? But 2 words, who cares? We don't care what happens to number 3. Not yet. Okay, that might come later, but not in this question. So we calculate F21, get a number for it. Calculate F31, get a number for it. Then when we add them up, we just have to make sure when we add them up that F21 is what? F21 would be negative, right? Because to the left. Question? Said you were confused?
Oh, I was talking about C.
What's C asking you?
Well, no, we got to see that. What's the vector?
Yep.
We go to the right or left?
Number 3 or C?
Oh, wait.
Let's look at the force on. Okay, I'm going to draw that on the same diagram up here, okay? The force, this is C, the force on number 3. Okay? 1 and 3, opposite charges, right? So they're going to attract. 1 is pulled towards number 3, 3 is pulled towards number 1. We'll call that F13. Okay? Now 2 and 3, opposite charges, right? 2 is pulled toward number 3, who cares? 3 is pulled towards number 2, we'll call that F23. So in question C, they're both acting to the left. Now, you'd have to be careful here. Force of 1 on 3 has a distance of both of those combined, right?
Yeah.
0.045. Does that make sense? Okay, give you another minute here, and then I want to do one more example, and then we'll call it a day. One more example with you, example number 4, which might look like it's way harder than the other ones. It isn't. We do the same thing here as we did with the last example and with worksheet number 7, question number 1. We draw a free body diagram, and we add the forces. We just have to add the forces a little differently because it's in 2 dimensions here, okay? Let's draw the free body diagram. Let's call this A, this one C, and this one is B. The net force on B due to A and C. Let's look at A and B first. A and B, they are like charges, right? If they're like charges, they're going to, Sydney, if they're like charges, they're going to do what? Attract or repel. Good. So that means that B is going to be pushed away from A. I'll call that FAB to the right. Good? Now, A is going to be pushed to the left, right? But, David, I don't care. It doesn't matter that it's pushed to the left, right? Unless we're trying to find the force on A. What about C on B? C and B. C is negative, B is positive. They're going to negative and positive are going to attract, right? So B is attracted towards C. We'll call that FCB. C is pulled towards B as well, right? But, David, right. You're actually sounding like you don't actually now as I ask you more and more. What comes next? What comes next? Find the forces, right? The good news is, if you notice example number 3 and example number 4, it's all the same numbers. So we don't have to recalculate anything here, right? We know FAB, like we could calculate it, QAB, QA, QC, QA, QB over R squared, or this time we can just write down the number. 0.01348 newtons. And FCB .00, nope. Let's try that again. 0.01198 newtons. And then we just combine them, right? Add them, but add them vectorially. You know how to solve for F right now, right? The Pythagorean theorem works out to be 1.8 times 10 to the minus 2. And theta, using the inverse tan function, works out to be 15.8 degrees. Now, don't, no, it's not. It's not 15.8 degrees. 41.6. Anybody else get that? Nobody's calculated it? I'm not going to say that's south of east, because that's not really a frame of reference here, right? It's just, you could say down from right, I suppose, but if you have it labeled on your diagram, it's fine. Just leave it like that. You see how many things kind of tie together, right? Like how the tool of vector analysis, like we did that last unit, right? Now we're doing it again. It's not any different, right? Except we're combining forces instead of momentums or velocities or whatever. It's amazing how many things actually are completely different topics, but use the same kind of technique. Okay, here's what I would love for you to do for homework tonight. Worksheet number 7, questions 1 and 3. Not 1 to 3, not 1, 2, and 3, 1 and 3. Here's the good news. Number 3 is like this, where you'll just be repeating some calculations, but in 2 dimensions. So you're not going to have to find all of those forces again. Just pick the forces that you've already solved for in another question and do the Pythagorean theorem and the inverse tan function with them. So it should go fairly quickly for you.